Hi, and a good day to all students. Hello, everyone, and welcome to our today's session. Today, what we will learn about hardness testing, one of the most important testing in determination of material properties. So, what does it mean by hardness? Hardness is a property of material that enables it to resist plastic deformation, penetration, dentation, and scratching. And that is the reason why hardness is very important from a material science standpoint, because resistance by resistance to wear by either friction or erosion by steam, oil, and water generally increase with hardness. So hardness is a characteristic of material, not a fundamental physical property, and it is defined as the resistance to indentation, and it is determined by measuring the permanent depth of indentation. Or we can simply say that when using a fixed force or loading and a given indenter, the smaller the indentation, the harder the material. The indentation hardness value is obtained by measuring the depth or the area of indentation using one of the over 12 different test methods available. So as we can read here, a large hardness means resistant to plastic deformation or cracking in compression, and a better wear properties. So the hardness of material is quite complex property and depend on the grain size, yield strength, tensile strength, ductility, resistance to abrasion, and many more. And as we can see in the scale here, we have an increasing hardness of different types of materials. Most plastic considered to have low hardness, and we have the material here, the diamond, that has the highest hardness among other materials. So here we have examples, different types of hardness testers. Hardness testing machine perform three common kinds of scientific hardness testing. We have a Brinell hardness testing, we have a Brinell, and we have a Rockwell, and we also have a Vickers hardness testing. Among these three types of testing, the Rockwell hardness test is the most widely used technique because it is easy to carry out and more precise than other kinds of evaluation. Renal hardness testing is typically used to evaluate materials that are too coarse materials, or that have an exterior that is too rough for other types of other test techniques. We will talk more about these three different types of hardness testing, the differences between these different types of testing, and so on later. Hardness testing is an extensively used form of material testing. It is comparatively quite easy to perform, easy to understand, and typically completely or quite minimal, or we can say it is non-destructive. And also most of the instrumentation is relatively cheap when compared to other types of material verification equipment. Furthermore, it can typically be carried out directly on the component without major alteration. And here are some application of hardness testing in terms of a material characteristic. We can use a hardness testing to test to check the material, test the hardenability, test the conform process, and also can be used to predict the tensile strength. And in terms of the functionality of the materials, we can apply a hardness testing to confirm the ability to function as designed. Can also use to determine the wear resistance, to study the toughness, and also the resistance to impact. The application of hardness testing will enable us to evaluate the material properties such as strength, ductility, and wear resistance. And so it helps us to determine whether a material or the material treatment is suitable for the purpose that required by the application. Um, the definition of hardness testing is a test to determine a resistance material exhibit to a permanent deformation by penetration of another harder material. However, hardness is not a fundamental property of material like what I have mentioned before. And therefore, when we want to draw a conclusion out of a hardness testing, we should always evaluate the quantitative value in relation to the given load of the indenter, specific loading time profile, and a specific load duration. And also specific indented geometry. Okay, sorry for my handwriting here. I hope you can understand it. So therefore, when we want to draw a conclusion of a hardness testing, we should always evaluate the quantitative value in relation to the given load of indenter, a specific loading time profile, and a specific load duration, and finally a specific indenter geometry. And here we have different types of hardness testing technique. And the most commonly used and basic definition is the resistance of material to a permanent plastic deformation. Hardness testing is measured by loading an indenter to a specified geometry and properties. Hardness testing, we measured it by loading an indenter. This is an examples of indenter for different types of hardness testing. So we load an indenter of a specified geometry, like what we can see here. We have different types of shape of indentation for a particular type of testing. We use that indenter onto the material for a definite length of time and measuring either the depth of penetration or a dimension of the resulting impression or indentation. Resulting impression or indentation. And the depth of penetration or indent dimension become larger as the materials being tested is softer. And common hardness testing varieties include Rockwell, like what we can see in the table here. Yeah, this is the most frequently used method due to its ability to produce a quick result, and is usually used on alloys and metals. And we have a noob and a viscous testing. We have a noob and viscous testing that is more ideal for a coating, thin materials, and a mounted metallographic component. And finally, we have a renal testing testing technique that we can apply for a large steel framework, cast iron, and aluminium. Okay, now we move on to the viscous hardness testing method. The Vickers hardness test method, also referred to as a micro hardness testing method, micro hardness test method, is mostly used for a small part, a thin section, or a case depth work. And this method is based on the optical measurement system, the micro hardness test procedure, like what we have in ASTM, American Standard Testing, American Society of Testing Material, E384, that specifies a range of light loads using a diamond indenter, like what we have in the figure here, to make an indentation which is measured and converted to a hardness value. It is very useful for testing what type of materials, but the samples must be highly polished to enable the measuring the size of the impression or indentation. And a square-based pyramid-shaped diamond, is used for testing in a Vickers scale, and typically loads are very light, ranging from 10 gram to 1 kilogram force, 10 gram to 1 kilogram force. Although micro Vickers loads can range up to 30 kilogram or more. So the micro hardness methods are used to test on metals, ceramic, composites, almost any type of material. And since the indentation is very small in Vickers testing, this is the examples of materials during Vickers hardness testing. It is useful for a variety of application, especially when we want to test very thin materials like foils, or measuring the surface of a part, small parts or small areas, when we want to measure individual microstructure, or measuring the depth of cast hardening by sectioning a part and making a series of indentation to describe a profile of the change in the hardness. The force F Okay, the force F is taken, and the diagonal, like what we can see in the figure here, the diagonal of the impression or indentation are measured. This is the real picture of diagonal of impression or indentation taken by microscope. And the mean of these two values, D, is used to determine the hardness, HV, of the material. And this is the equation that we use to determine the Vickers hardness number of material. F refers to a force that we apply during the testing, and D is the length of the diagonal of the impression or indentation. And theta equals to 136 degree. Now we move on to Rockwell hardness testing. The Rockwell test determine the hardness by measuring the depth of a penetration of an indenter under a large load compared to the penetration made by a preload, as defined in ASTM E18. This is the most commonly used hardness test method. It is generally easy to perform, more accurate than other types of hardness testing method. It measures the permanent depth of an indentation produced by the force or load on an indenter. Rockwell test is designed as a method of hardness testing for a rapid comparative analysis between different types of materials or samples. And the depth of impression or indentation that measured and rated on a dial calibrated inversely into a 100 division. A deep impression will result in a low value, which implies a soft material. And a hardened steel ball indenter used with a diameter of 1/16 inch, 1/8 inch, 1/4 inch, and ½ inch, and standard indenting loads are 60 kilogram, 100 and 150 kilogram. And here we have illustration of test methods for hardness. First, preliminary test force, commonly referred to as a preload or a minor loading, is applied to a sample using a diamond or ball indenter. This preload breaks to the surface to reduce the effect of a surface finish. And after holding, the preliminary test force for a specified dwell time. The baseline depth of the indentation is measured, like what we can see in the figure here. And after the preload, an additional loading called the major load is added to reach the total required test loading. This force is held for a specific time, a predetermined amount of time or dwell time, like what I have mentioned before, to allow for elastic recovery. And this major load is then released, returning to the preliminary loading. And after holding the preliminary test force for a specified dwell time, the final depth of indentation is measured, and the Rockwell hardness value is derived from the difference in the baseline and the final depth measurement. Like what we can see in the figure here, D refers to the distance measurement taken, representing a difference between a preload and a major load position. And this distance is the value that we use to calculate the Rockwell hardness number. When we want to select a Rockwell scale, a general guide is to select the scale that specifies the largest load and the largest indenter possible. Without exceeding defined of operating condition. Without exceed defined. And this condition include test specimens that are below the minimum thickness for a depth of indentation, a test impression that falls too close to the edge of a specimen, or another impression or indentation, or a testing on a cylindrical specimen like this. And in addition to that, the test axis should be within 2 degrees of a perpendicular to ensure a precise loading. And there should be no deflection of there should be no deflection of a test sample or a tester during the loading application from condition such as dirt under the testing specimen or on the elevating screw. And it is also quite important to keep the surface finish clean, and decarburization from heat treatment should be removed to ensure that the value of hardness that we get is precise. Okay, now we move on to the Brinell hardness testing. The Brinell hardness test method, as used to determine the Brinell hardness, is defined in ASTM E10 Yeah, and it is most commonly used to test materials that have a structure that is too coarse or that have a surface that is too rough to be tested using other test method. For example, uh, casting and forging. Brinell testing often use a very high test loading, equals to a 3000 kilogram force and a 10 millimeter diameter indenter, so that the resulting indentation averages out most surface and subsurface inconsistencies. So in the Brinell hardness testing, a hard steel sphere, like what we can see here, usually 10 millimeters in diameter, is forced into the surface of the materials. The diameter of the impression or indentation here, typically ranging from 2 to 6 millimeters, is measured, and the Brinell hardness number, abbreviated as HB or BHN, HB or BHN, Brinell hardness number, uh, is calculated from the following equation. Yeah, we have a 2F divided by pi d times d minus d to the power of 2 minus d sub I to the power of 2 square root, where F is the force in Newton and d is indenter diameter in millimeter, and small d or d sub I equals to indentation diameter in a millimeter. And the Brinell hardness has the unit of a kilogram over millimeter squared. This is the unit of so we have many types of a technique to determine the hardness of material. We have a Vickers, Brinell, Rockwell, and we also have other methods that we don't include in our discussion here, such as Mayer and Leap testing. Although it is quite possible in many cases to give an exact conversion, it is possible to give an approximate material specific comparison table for uh, materials such as steel. So here we can use the scale. This is the scale that we can use to convert a value that we get from one type of a testing to another type of a testing. This is from ASTM E140, a standard hardness conversion tables for metals relationship among Brinell hardness, Vickers hardness, Rockwell hardness, superficial hardness, loop hardness, and scleroscope hardness. And we can use this scale to convert a value that we get from one type of testing to another type of testing. And it's good to know that hardness numbers are used primarily as a qualitative basis for comparison of materials, specifications for manufacturing and heat treatment, quality control, and correlation with other properties of a material. And both hardness and tensile strength are indicators of a metal's resistance to a plastic deformation. For example, for materials such as cast iron, steel, and brass, the two are roughly proportional. For example, we have a Brinell hardness. It is related to the tensile strength of steel by approximation. in the equation here. The tensile strength in PSI equals to 500 times Brinell hardness. This is the equation. If we want to approximately correlate between hardness and a tensile strength of material. But we have to remember that the relationship between the hardness and strength definitely depend on the microstructure of the material. The nature of this microstructure dependence is usually explained to a different work hardening characteristic of materials with a different grain structure. Texture also plays a very important role here. So we need to know that what a tensile strength and hardness signifies physically, what are differences between these two. And if you still remember from our previous lecture, the tensile strength, it gives us the material bulk property like toughness, or in other words, the resistance of a material to a breaking under tension. And for hardness testing, it gives us the material surface property. Like a scratch resistance, or in other words, resistance to indentation. So that's it all about the fundamental of hardness testing. Thank you.